Howdy. This is Mr. Potter. In today's lesson, we're going to be talking about vector calculus. We're going to be talking about it from a two-dimensional perspective. If you want to get a three-dimensional perspective, then you really need to take a look into a Calculus 3 class. But we're going to be looking at vectors from a two-dimensional perspective. And so I want to start by kind of talking about what a vector is. So when I talk about points on the xy plane, which we've been talking about throughout this course, if I'm talking about the point 4, 3, 4, 3 is a location on the xy plane. But if I want to talk about a vector has both magnitude and direction. So this vector is starting at the origin and headed towards this point. And so a vector is really describing moving from the origin to that point. Now notice that this motion is kind of in a northeasterly direction, and because of the Pythagorean theorem, I'm moving approximately 5 units in this direction. So I could take any vector that starts at any point, and by moving up 3 and over 4, any of these line segments that I draw, these directed segments, are all going to be parallel. They're all going to have the same length. So when I talk about a vector is a value that has both magnitude and direction. And what's really important to remember that a vector is not a position. What a vector is a path that we're going to be taking. Notice that all of these are describing the same path. They're just talking about the path from different starting points, and of course they're ending up at different ending points. But the path is the same. They all have the same direction. They're both headed in this northeasterly direction, and they all have the same angle from the horizontal, the angle that you would get in a 3, 4, 5 right triangle. And they all have the same magnitude. In other words, all of these vectors are all going to be the same length. They're all going to have a length of 5. So when I talk about a position being the point 4, 3, each one of these vectors has a component of 4 in the horizontal direction and 3 in the vertical direction. And the thing we're going to see is different is that we're going to be using these angle brackets rather than using the parentheses that we use when we're denoting a location. So vectors are going to be using these angle brackets. And when mathematicians publish vectors, they try and use bold. So you'll see a bold letter V. But it's going to be very difficult for us to draw a bold letter. So what mathematicians do when they're just writing these out is they'll write the letter V with an arrow above it, a ray above it, so that we can see that we're talking about not just a regular scalar quantity, a quantity that only has magnitude, but we're talking about a vector quantity that has direction. And this arrow is not saying that it's traveling to the right, it's just saying that this is a vector quantity. So I would say that this vector is the vector 4, 3. And so when we talk about these vectors, we're talking about the magnitude. Keep in mind these magnitudes are basically the hypotenuse of right triangles. So my magnitude is really going to be the square root of my horizontal component squared plus my vertical component squared. And that's how we were getting the magnitude of 5 of each of these, because these are essentially the hypotenuse of a right triangle. And the other important thing that we're talking about is when I'm talking about direction. So when I'm talking about direction, remember that direction, since I'm talking about this angle is a situation where I know the opposite leg and I know the adjacent leg. So I know that the tangent of our angle in particular is going to be equal to our vertical component divided by our horizontal component. And so I could say that theta, our direction, is equal to the arctan of my vertical component over my horizontal component, B over A. So I could try an example of this. I could look at an example like the vector radical 2 and negative radical 2. So when I'm talking about a vector like this, I'm talking about a vector that's going to be moving to the right a certain amount and down a certain amount. So I'm talking about a vector that's down here. It's important to note that we're talking about a vector in the fourth quadrant. So when we're doing our calculations, our magnitude of our vector, so if I call this vector W, then the magnitude of my vector, or in other words, the 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 symbols that we use for magnitude for this vector is going to be the square root of my horizontal component squared plus the square of my vertical component. So this ends up being the square root of 2 plus 2, which is 2. So in other words, this vector has a length of 2. And if I want to find the angle, I know that theta is supposed to be tan inverse of negative root 2 over root 2. But this is really tan inverse of negative 1, which is negative pi over 4. Notice, of course, because I'm dealing with this negative pi over 4, I am talking about an angle in the fourth quadrant. If instead I ended up with an angle in the second quadrant, where tangent is also negative, I would just have to basically translate this 180 degrees, or pi units. So that's how we deal with, when I have a vector, how do I find its components, its magnitude, and its direction. Now I could also talk about this from the standpoint of, what if I have the magnitude and direction and I want to find the components of my vector? Let's say that I know that my vector is 12 units long. At an angle of theta equals pi over 3. So if I'm looking at this from the angle of pi over 3, pi over 3 is this angle here, and I'm going to be 12 units long. So if I'm looking for the vertical component, the vertical component is my opposite, and this is my hypotenuse. So the vertical component is going to be 12 times the sine of pi over 3. And my horizontal component, because that's the x component, that's going to be 12 times the cosine of pi over 3. And so when I'm looking at this, my horizontal component is going to be equal to my magnitude times the cosine of theta. And my vertical component is going to be equal to the magnitude times the sine of theta. Now, of course, I know that cosine of theta is 1/2, so this is really 6. Sine of pi over 3 is radical 3 over 2, so I end up with 6 root 3. And so this is my component form of my vector, not my magnitude and direction form of my vector. But it's very easy to go both ways given these formulas. To find the horizontal and vertical components, I just take my magnitude and multiply by cosine theta or sine theta respectively. So when I'm dealing with vector, there's one real special case that we deal with, which is called the zero vector. In other words, the vector that has no horizontal component and no vertical component. And because of this, it has zero magnitude. But we actually have no direction. And more than no direction, this is actually an indeterminate direction, because following the formula, theta should be tan inverse of my vertical component divided by my horizontal component. And this we talked about in chapter 8 is an indeterminate form. And because there's no functions involved for x of t and y of t, there's no function involved here, then we can't really resolve this using L'Hopital's rule as we had done in previous problems. So we're kind of stuck with this idea of having zero magnitude in no direction. And some books, to be fair, say it's not no direction, it's every direction. Because I'm essentially talking about a point that really is going out in every direction, an amount of zero. So the zero vector is something that we need to be aware of because we do come across it on occasion. So what we need to talk about now is we need to talk about some of these properties of vectors. And one of the properties of vectors is that we can add vectors together. So given a vector, one vector that would be going at one particular angle, and one vector going at some other angle, not necessarily the same angle. Keep in mind that this vector has some horizontal component and some vertical component. And this vector also has some horizontal component and some vertical component. And so my result would be to kind of string these together head to toe and come out with a resultant vector. This resultant vector is the sum of two or more vectors. And of course, it starts at the original starting point and it ends at the original ending point. And something that's interesting to note is that the order doesn't matter. I could have put my gold vector down first, and then my maroon vector, and I end up at the exact same part because I'm talking about the diagonal of some quadrilateral. So the first property that we have is that I can take two vectors, v and w, and add them together. And what I end up with is I end up adding the horizontal components and adding the vertical components of each vector. Notice, of course, that I could have one of these or both of these components being negative. And it also holds true that if I wanted to subtract vectors, I end up subtracting the horizontal or vertical components. We also have something called scalar multiplication. And in our geometry classes, we call this dilation. The idea that we could scale a vector, either by multiplying it by a value to make it longer, or dividing by a constant value to make it shorter. So the idea is that if I have k times some vector, then what I'm really doing is I'm multiplying the horizontal aspect times k, and I'm multiplying the vertical aspect by k. And so this allows me to make a vector that's longer by changing its magnitude. But notice that the ratio of these terms are exactly the same, so I'm not changing the direction. All I'm doing is I'm making this vector longer or shorter, making it have a larger or smaller magnitude. And there's one other concept that we need to talk about, and that's the concept of a unit vector. Just like in pre-calculus, when we talk about a unit circle, it's very important to deal with the circle that has a radius of 1. It's going to be very important for us to deal with vectors which have a magnitude of 1. And if I wanted to find the unit vector for an existing vector, what I'm actually what I want to do is take this vector and kind of divide each of those horizontal and vertical components by the scalar value. In other words, I'm going to be taking this horizontal component and dividing by the square root of x squared plus y squared. And then taking the vertical component and dividing it by the square root of x1 squared plus y1 squared. So I can find a vector that has a length of 1, but still goes in the same direction that we're talking about, because the ratio of this divided by this is exactly the same as the ratio that we were dealing with before. y1 over x1. So, because this is a calculus course, and calculus is really dependent on functions, I need to introduce the concept of vector-valued functions. In other words, vectors that are dependent on a particular value. So I could talk about position vectors. In other words, I'm going to have some function r of t, where the horizontal component is going to be some horizontal function of t, and the vertical aspect would be some vertical function of t. In other words, the vector actually changes. And so what happens in this situation is that my vector is going to start here, and as t increases, my vector may get longer or shorter. But in essence, what's happening is I'm describing a path that this vector is taking. From some starting t to some ending t. And so when I talk about position vectors, I'm talking about a vector whose horizontal and vertical components are functions. X and y as functions of t. In other words, the parametrics that we were talking about in our previous video. And of course, because these are functions, I could talk about the change of t, the change of x with respect to t, and the change of y with respect to t. So I could talk about a vector whose components were x prime of t and y prime of t. And when I do that, I end up with a velocity vector, v of t. So this is velocity. And this allows me to find the vector that represents velocity at any particular time. And by that same token, I could take the second derivative of x and the second derivative of y and use this to find an acceleration vector at t. So at any particular time t, I can find the acceleration, its horizontal and vertical components. There's one other important thing that we need to talk about, and that's the concept of speed. Now, the thing to remember is that when we talk about speed, we don't have a direction that goes with speed. If I'm going 10 miles an hour, it doesn't matter if I'm going 10 miles an hour forward or 10 miles an hour backwards or 10 miles an hour straight up. I'm moving at a rate of 10 miles an hour. In other words, it's only a scalar value. It's not going to be a vector, so it's not going to have two components. It's just going to be a number. And the way we find speed is if I know the horizontal speed and I know the vertical speed, then the actual speed that I'm traveling would be the magnitude of this vector. In other words, the square root of x prime squared plus y prime squared. So my speed component, my scalar, is going to be the square root of x prime squared plus y prime squared. So I have these different things that I can do to determine the position or the speed or the acceleration or the velocity at a particular time t. And so I want to do an example of this. So I'm going to start by giving you a displacement function. So r of t, this is my position, is given by the quantity 3t squared, comma, e to the negative t. So I've got a function that describes this variable at a particular time. If I wanted to find the velocity at a particular time, I'm going to be taking the derivative of each of these components. So the derivative of 3t squared would be 6t, and the derivative of e to the negative t would be negative e to the negative t. And if I want to find acceleration, I'm going to be taking the second derivative here. So the second derivative is the constant 6, and the second derivative here would make this again positive e to the negative t. And finally, once I've done this step here, I can actually take a little segue and talk about the speed, because the speed is a scalar, but it's going to be the squares of each of these components added together. So it's going to be 6t squared plus negative e to the negative t squared. So as long as I know one of these quantities, I certainly can move down and take the derivative to find velocity, take the second derivative to find acceleration. And if I know the velocity vector, then I can certainly come across here and use its components to determine the speed. And this speed is really a speed function. This is the speed at time t. So that's one way to look at vectors. But another way that we can look at vectors is to determine the displacement and the distances traveled. So here I'm assuming that I've got some velocity vector, which is going to have a horizontal component and a vertical component. And what I can do is I can determine the displacement. And my displacement can be determined by finding the integral of velocity, because the antiderivative of velocity is displacement. And the integral of v2 of t dt. What's important to note is that as I'm going from time A to time B in both of these quantities, this tells me how far I've displaced myself from position A to position P. And what's also important to note is that these are points, not vectors. These are locations. In other words, I've got to have my location at A and my location at B and subtract the two. So in other words, I'm going to have to be given some starting position, x of A, y of A, which I'm starting at in order to determine this displacement. Now keep in mind, I'm not only talking about displacement here, but I'm also talking about the distance traveled. So if I take 5 steps forward and I take 5 steps back, even though I'm right where I started, I've traveled a total distance of 10. 5 forward and 5 backwards. So in other words, I don't care about the direction when I'm talking about the distance traveled. I only care about the magnitude. So when I'm talking about the distance traveled, what I'm actually doing is I'm finding the integral from A to B of the speed. Now, if that looks familiar, it really should, because this v1 that I'm squaring and this v2 that I'm squaring, those really are the derivatives that we were talking about when we were doing arc length. And in fact, this is the arc length formula. The distance that I travel along a vector-valued function is the same as the arc length for that vector-valued function. So I want to do one more example here. I want to take a look at a particular situation where I'm starting with velocity vector that's equal to 3t squared and 1 plus cosine of pi t. And I know that I'm going to be starting at an initial position of 2, 0 at time t equals 0. And I want to find the displacement at t equals 3. And then I also want to find the distance traveled at t equals 3. I can do both of these using the formulas that we talked about on the previous page. So to find the position, I'm going to want to find the integral from 0 to 3 of 3t squared. And that's going to involve my horizontal position. And then I'm also going to find the integral from 0 to 3 of 1 plus cosine pi t dt. That's going to allow me to find my vertical position. And so this is going to end up being a point that I'm going to be reached at. Notice that I have this initial value at 2. When I do an integral, I really end up with the position at 3 minus the position at 0. So if I want just the position at 3, I want to add these quantities in. These quantities are really my constants of integration. So the antiderivative of 3t squared would be t cubed, which I'm evaluating from 0 to 3. And I'm going to have to add 2 to this because this is my displacement. That's going to take care of this term, make it go away, and really find the position when t equals 3. And I'm going to need to do the same thing over here. This is going to be t plus the sine of pi t over pi, which I'm evaluating from 0 to 3. And adding zeros is not going to change anything here. So this ends up being 3 cubed, which is 27. And this is going to end up being 3 plus the sine of 3 pi, which is negative 1 over pi. So this is 3 minus 1 over pi. So what I found is I found my position at a particular point. But now I can also find the distance traveled, and my distance traveled is going to be the integral of from 0 to 3, the square root of 3t squared plus 1 plus cosine pi t squared dt. Now, one of the things that we've noticed when we've worked these types of problems that these are not the type of problems that you can easily do the antiderivative of. So using our technology, you find this antiderivative actually ends up being 19.343 units. So that's the distance that we end up traveling here. Vector valued functions are very important, and if you continue in calculus, you'll actually see a lot more applications of vectors. But what we're talking about in this course is we're talking about it from a two-dimensional standpoint. And we're talking about the context of getting from position to velocity to acceleration and back. That's really the context that we're dealing with when we're dealing with AP vectors. So, this is Mr. Potter. Thank you for watching. Have a great day.